Continuing our discussion of flow in pipes, now I want to do some examples of computation of head loss in laminar flows, turbulent flows, and how we account for minor losses in systems. So, first example, oil is flowing in a horizontal pipe in laminar flow. The flow rate is given, specific gravity and viscosity, and if we have a head loss of 12 centimeters over a pipe length of 3 meters, the diameter of the pipe is most nearly which of these alternatives? So in this case, we're given that the flow is laminar, so automatically we know that this is Poiseuille flow, for which this equation applies, the relationship between the pressure drop and the flow rate, etc., in the pipe. Now, in this case, we're given that the energy grade line here is sloping downwards and it drops by a height of 12 centimeters. How do we relate that to the pressure drop in the flow? Well, remember that the hydraulic grade line is below the energy grade line by a height equal to the local velocity head, v squared over 2g. And the distance from the pipe center line to the hydraulic grade line is the local pressure head, P over gamma, which I'll call P1 over gamma here. Now, in this case, the diameter of the pipe is constant, therefore the cross-sectional area is constant, therefore the velocity is constant, therefore v squared over 2g is constant, therefore the hydraulic grade line is parallel to the energy grade line. And the drop in the energy grade line is therefore equal to the drop in the hydraulic grade line. But the drop in the hydraulic grade line here, if the pressure head is P2 over gamma, the drop in the hydraulic grade line is the drop in the pressure head, P1 over gamma minus P2 over gamma, which is equal to delta P over gamma, where delta P is the pressure drop in the pipe. So in this case, you can see that delta P over gamma is equal to the drop in the pressure head, or the energy grade line rather, which is 12 centimeters. So therefore, we have this equation here. The pressure head loss is the drop in the energy grade line, is delta P over gamma, is equal to 128 mu LQ over gamma pi d to the fourth. In this case, we're asked to calculate the diameter, so rearranging that equation to make d the subject, we get that. And now we can substitute in the numbers. 128 mu is viscosity is 0.38, etc. And the answer is the diameter is 0.10 meters or 10 centimeters. So the answer is B, 10 centimeters. In this example, we have water being pumped at a rate of 0.083 cubic meters per second through a 20 centimeter diameter pipeline, and the relative roughness is given as 0.01. The water viscosity is given, and the question is, the friction head loss over a pipe length of 45 meters is most nearly which of these alternatives? So, firstly, we would like to know whether the flow is laminar or turbulent. And to do that, we compute the Reynolds number of the flow, rho v d over mu. And first we need to get the velocity, because in this case we're given the volume flow rate and the area. So the velocity is q over a is equal to q over pi by 4 d squared, which is 2.64 meters per second. And then the Reynolds number is equal to rho, which I'm assuming is 998 kilograms per cubic meter, times the velocity, 2.64, times the diameter, divided by the viscosity, which is given, and the Reynolds number is 5.92 times 10 to the fifth, so the flow is very obviously and very definitely turbulent. The relative roughness we're given, the relative roughness is epsilon over d, is 0.01. So now the question is, what is the friction factor, which is a function of epsilon over d, for these two values of Reynolds number and relative roughness? So for this, we turn to the Moody chart here. So the Reynolds number is approximately there, approximately 6 times 10 to the fifth. The relative roughness, 0.01, is right there. Looking at the intersection of those two curves And reading off on the left-hand side, we see that the friction factor for this situation is 0.038. Next, we turn to the Darcy-Weisbach equation, HF equals FL over D V squared over 2G, and now we can evaluate that. F we've just found is 0.038, pipe length is 45, diameter is 0.2, etc., which gives me a head loss of 3.04 meters, so the answer is A. Now, next I want to look at minor losses, which are other losses in the system separate from friction head losses, and they would be due to valves, elbows, other accoutrements in the setting. So this is the term HM for minor losses, and typically we express a minor loss by an equation such as this one here. HM is KL V squared over 2G, where KL is a so-called loss coefficient. V is a local reference velocity, so V squared over 2G is a local velocity head. Here is the corresponding section in the reference manual where they express the minor losses. They call it HF for a fitting, but a more common term is a minor loss, and the coefficient they express here as C, the loss coefficient. And the value of the loss coefficient, generally speaking, is not something you can predict. You have to look it up in tables or manufacturers' handbooks, etc. For example, different types of valves. Here are some examples of valves, globe valves, angle valves, gate valves. Of course, the loss coefficient depends on whether on how open the valve is, or other examples for entrance losses from flow from a large reservoir or a large pipeline into a smaller one are given here. So a re-entrant entrance like this has a very large coefficient, whereas a nicely flared one here has a very small energy loss or a very low loss coefficient. In this example, we have water flowing by gravity between two reservoirs of different elevations. We're given that the elevation difference between the two reservoirs, this height difference here, is 5 meters. The pipe diameter is 50 centimeters, the length is 500 meters, and the friction factor is given at 0.02. We have a valve here with a loss coefficient of 2 situated in the pipe, and the question is, neglecting other minor losses, the velocity in the pipeline is most nearly which of these 4 possible answers? So we applied Bernoulli equation between the two water surfaces, and I'll label the water surface in the upper reservoir as 1 and the water surface in the lower reservoir as 2. So here is our generalized Bernoulli equation, accounting for any energy losses and gains between the two systems, where we have P1 over gamma plus V1 squared over 2G, etc., is equal to, and then our terms for head losses due to friction, head gains due to pump or loss due to turbine, etc. So in this case, we can simplify this equation considerably. At the free surface at 1, the free surface is in contact with the atmosphere, so the pressure there is atmospheric, which is 0. If the reservoir is large, we have the velocity in the reservoir is 0. Similarly, at the lower reservoir, the pressure at the free surface is 0 and the velocity is 0. We have no pumps in the system, so the head gain due to the pump is 0. Similarly, we have no turbines in the system, so HT is equal to 0. So rearranging, we have the elevation difference between the two reservoirs, Z1 minus Z2, which is equal to capital H, is equal to the head loss due to friction plus the minor loss. So substituting the equations then, the head loss due to friction is given by the Darcy-Weisbach equation, FL over D V squared over 2G. The head loss due to the valve is given by the minor loss coefficient KL multiplied by the velocity head V squared over 2G. Or rearranging, we have H is equal to F L over D plus KL multiplied by V squared over 2G. So in this case, the unknown is the velocity. So rearranging that equation in terms of the velocity in the pipeline, we have this equation. V is square root of 2GH divided by FL over D plus KL. Substituting in the values, we have 2. G is 9.81. The elevation difference is 5 meters. The friction factor is given as 0.02. Length 500. Diameter 0.5. And the minor loss coefficient is 2. So calculating that out, we have the velocity in the pipeline is 2.11 meters per second. So the closest answer is B. And this concludes our examples on calculating head losses in pipe systems.